I have always been fascinated with geography and the idea of visiting every country in the world. This fascination led me to spend countless of hours playing Geoguessr. Geoguessr is an online game that challenges players to identify their locations based on Google Street View images. The game places you on a random road in the world with the objective of pinpointing this location on a map. At first glance, this task can seem daunting, but clues like national flags or recognisable languages can provide valuable hints. In this game, precision is rewarded. The closer your guess to the actual location, the higher your score. The scoring system fosters a competitive environment that has even given rise to a professional Geoguessr community. Inspired by my passion for this game, and tasked with developing a project for my Design Intelligence Agents course at university, I chose to explore a similar concept. Can a basic intelligence agent outperform the average human score on Geoguessr? Understanding the core technologies and theories behind AI and geographical image recognition is essential for grasping the complexities of this project. At the heart of the project is a deep learning technique that is used for its enhanced ability within image recognition tasks. A convolutional neural network, or CNN as it will be known in this video, is the brains behind the whole system. They are highly effective at understanding and interpreting visual imagery. This helps to pick out and identify specific geographic locations from recognisable patterns. The intimate workings behind them will be explained later on when we talk about the model. Early studies in AI-based image recognition set the stage for using neural networks for geographic analysis. For instance, research by Tobias Wayland, Ilya Kostrikov, and James Philbin in 2016 demonstrated how neural networks could be trained to geolocate images from millions of test data. More recent developments have focused on improving the accuracy and efficiency of these systems. For example, research from Parallel University in 2024 introduced modifications to CNN architectures that added transfer learning to significantly enhance the performance of the AI systems within urban environments. Before diving into this work, a lot of preliminary research was done and conducted with papers based on dropout and image augmentation to papers using feature fusion, all of which will be linked below for any further reading. This project harnesses TensorFlow and MobileNet v2, using pre-trained ImageNet models to significantly enhance the AI's learning efficiency and accuracy. These tools were pivotal in developing a simple AI system that can quickly and accurately process geographical information from images. The first major considerations were where the bot will be operating and how the training data will be collected. The easiest way to collect geotag data is using Google Street View's API tool. This left the question of where these images would be stored before training. Due to the vast quantity of images needed for training, I didn't want to store them locally on my laptop, so I decided to use a Google Cloud bucket to host them all. This system meant that during the training, the bot would have to access the internet and download all the images, slightly increasing training time. However, this saved a lot of space on my computer, so it was definitely worth it. Due to the limited training data and the basic bot being used, I decided to simplify the project down to one country, and with Google's rules only allowing for 28,500 images per free account, this training set was limited to stay completely free. Using all the images in one country will provide zero chance of error or wanting to change countries. Therefore, an initial cap of 15,000 images was set for the first batch, making sure that a positive trend could be observed in the bot before moving forward. Due to the small number of images that could be used, it was initially thought that a very small country should be chosen. After the initial considerations of Portugal, Greece, New Zealand, Japan and Switzerland, I opted for Switzerland for several reasons. Geographical diversity. Switzerland, although small, offers a varied landscape that includes mountains, lakes and flat areas. This diversity is crucial for pattern recognition systems that AI will use. Manageable area. With an area of approximately 41,290 square kilometres, Switzerland's compact size allows for thorough coverage, unlike New Zealand, which is nearly 6 times larger. Challenge appropriateness. Switzerland presented a balanced difficulty level, in contrast to Japan, due to its high average score in Geoguessr, showing there is plenty of human visible cues that the AI might not pick up on. Whilst most countries fit 2 of this criteria, Switzerland fit all 3, making it the obvious choice. After Switzerland was chosen and the training data was downloaded, the model was then created and trained. The training accuracy graph shows a very low accuracy, which slightly worried me, but I knew it wouldn't be spot on from the start. Therefore, I likely very over-optimistically ventured into testing the bot out. However, despite Switzerland's extremely diverse landscape, I hadn't accounted for the fact that there are very few roads up in the mountains or by the lakes. Therefore, this led to all the images having minimal distinct features, causing the bot to struggle to distinguish between similar geographic locations. Most tests returned predictions concentrated in just a few areas, far from the expected diversity of locations. Faced with these limitations and insights from initial tests, I decided to pivot to a new focus. The United States offered more extensive and varied datasets, allowing for the implementation of more sophisticated AI techniques. This decision marks a significant shift in the project's direction, which I will detail in the next segment. Following the decision to change to the US, the AI system had to undergo a complete redesign, and I effectively started from scratch. The first point of call was retrieving an entire new set of training data. Due to the previously spoken about cap, I set a limit of 10,000 images for the first attempt. This low number of images for such a vast country was worrying, and required precise and strategic data handling to get the most out of each image. Next, a full API call rework was required to obtain these images from within the US. Firstly, a new Google bucket file was created to host these images. Then, a set of random coordinates within the US were generated to retrieve a random image. The metadata for those specific coordinates is then accessed to see if there is a valid Street View image for that location or not. If an image is available, it's downloaded to the bucket, and if it is not, it's forgotten about and the system restarts. When the image is downloaded, it's saved with its coordinates as its name, so that later on it is easy for the training system to know the location of each image. Now that the images have been downloaded successfully, the task of how the bot will predict a location arose. Initially, I was a little stumped here, as I wasn't quite sure how a bot could just predict an exact location. However, after doing some research, I came across this video by a dumb on YouTube. This video is also where the idea for some of the visual plots that you'll see later came from. In this video, he describes how by splitting a country into a grid-like structure, you can have an AI bot predict which grid tile it thinks the image most likely belongs to. This approach seemed to work well, and so I split the US into segments of 10 by 10 squares. I theorised that there wasn't enough training data available to be accurate in splitting the country up anymore. I also identified and excluded grid areas outside the mainland US, such as bodies of water or neighbouring countries, to enhance the focus and accuracy. This was done by working out which grid sections weren't needed and then adding them to a list. There's a lot more that comes into the prediction logic, but we will discuss that later on as it doesn't relate to the bot being created. Next, the images need to be pre-processed to ensure they're ready for training. Each image within the bucket is iterated over and a regex command called to search for the coordinates within the names. The coordinates will then turn into grid positions for each image so that the bot can train itself. There were adjustments made to accommodate for the standard input size of our computer vision model, which is 224 by 224 pixels. Despite considering image augmentation, which mitigates biases and enhances model robustness by rotating or editing the exposure of some of the training images, I decided against this due to the fact that the training images were the exact same as the test images, so it likely just confused the bot. Now, an AI is only as good as its training data, therefore you need a vast quantity of it and to make sure that all areas are covered. We can see from this plot, where each dot is one of the original 10,000 images, that virtually the whole United States is covered, and there is no significant area that's been left out, meaning the model is as robust as possible. Next, the model needs to be built. As stated earlier, I used a convolutional neural network for this. Renowned for its effectiveness in analysing visual imagery, the CNN architecture incorporates several layers. Convolutional layers. These layers apply filters to detect key features such as edges and textures through convolution operations. Activation functions. Non-linear functions, like ReLU, enhance the network's ability to learn complex patterns. Pooling layers. Average pooling was used to reduce dimensionality, simplifying the network's computations without losing critical information. Fully connected layers. The culmination of the CNN. These layers integrate learned features to make final predictions, with each of the 100 neurons corresponding to a specific grid box within US. This is a brief introduction to CNNs, however they are so useful and much more complicated. Lots of my learning on this topic has come from a video series from 3 Blue 1 Brown, along with plenty of papers which I have linked in the description below if you want to find out more. The model leveraged TensorFlow and MobileNet v2's architecture, which is pre-trained on the ImageNet dataset, providing a robust foundation for feature recognition. Training involved techniques like early stopping to prevent overfitting. This is required to stop generalizing. For example, imagine whilst revising, you memorize a question, come to the real test and a similar question comes up. However, you assume it's the same one and just write down the answer without checking. This is overfitting. The training set was split into 80% training, 20% validation, allowing for continuous performance assessments and adjustments. The training sets are split into batches and epochs, which represent the number of images being used at one time and the number of times looking at all the images. Here you can see how the bot got more and more confident in its guesses the more time it spent learning. The darker the darkest box, the more confident the bot is with its prediction. We can see that at the start, the bot seems to be picking random locations, but as it started to learn, it got more and more confident in specific locations. Finally, we can see that the bot started to get really confident with its guesses as it got more robust. In the initial testing phase, it was encouraging to see that the bot could distinguish between distinct environments like deserts and forests. However, despite these promising signs, the AI's performance was still suboptimal. It consistently scored around 5,000 points per round, which is far from the target of over 11,000 points required to surpass human players. This indicated that while the foundational model was operational, it necessitated significant refinement to enhance its accuracy and effectiveness. AIs don't inherently work by selecting one option. They will always have a few answers and give them all as confidence scores based on how likely it presumes each option is. This is exactly what the shadows are in the boxes. This can be taken to improve the final prediction. The initial method involves selecting the centre of the most likely grid box. I adapted the model to utilise a weighted average approach for its prediction. Instead of simply choosing the most probable location, the model calculates a weighted average based on the confidence levels across all potential grid boxes, thereby producing a more nuanced and precise location output. Although this method skewed predictions towards the centre regions of the US, it marked a considerable improvement in the model's ability to generalise across different geographic features. One notable issue with the weighted average approach was its tendency to underrepresent coastal locations. Specifically, Florida posed a unique challenge due to its geographical and botanical features that misled the simplified AI. The peninsula's limited adjacent land areas skewed the weighted average away from it, complicating accurate predictions. To counteract this, I considered implementing a region-specific adjustment for such outliers, although this risks complicating the model further without guaranteed improvement. Throughout the optimization process, I experimented with various configurations of the neural network, adjusting the number of layers, filter sizes, and network depth to balance between computational demands and predictive performance. Hyperparameter tuning was also critical, with adjustments made to the learning rate, batch size, and number of epochs to optimize training. These adjustments were validated through a series of preliminary tests, which demonstrated significant improvements in location prediction accuracy. Encouragingly, after several iterations, the model achieved a breakthrough, surpassing the average human score in test runs. Additionally, the unexpected increase of available Google Cloud credit allowed for the inclusion of 30,000 images in the training process. However, computational limitations on my laptop required reducing this number to 22,000 usable images. The final dataset was used to train the last iteration of the model, which then proceeded to comprehensive testing. With the AI model now optimized for the US and delivering accurate predictions, let's explore the web application that facilitates the user interaction with the bot. This app, designed as a virtual environment for this project, simplifies the process for uploading and analysing images. Users are prompted to upload an RGB image. Images with the alpha channel are not compatible due to the training specification of the model. Once uploaded, the app displays the predicted location on an interactive map, which the users can zoom in and out of to view the AI's guess in greater detail. Additionally, users have the option to view the location in Google Maps or to explore the AI's confidence levels through the Show Uncertainties feature. This feature displays a matlib plot visualization of the US, with the predicted location highlighted in magenta, surrounded by boxes shaded according to the AI's confidence level. The darker the shade, the higher the confidence. This interactive approach not only makes the application user-friendly, but also allows to visually grasp the AI's prediction logic and reliability. With the AI system now finely tuned and optimized, it was time to move on to testing, to finally answer the question, can a basic intelligent agent outperform the average human score in Geoguessr? To make a fair and thorough test, I decided to play 4 games with this version and get an average score. The first game was actually the best of the 4, so let's see how it went. The game started in a fairly green rural setting. After uploading an image of this location to the app, the AI predicted it to be Illinois. This guess was impressively close, only 125 kilometers away from the actual location, earning 4,306 points. A promising start, considering the maximum for each round is 5,000 points. Next, we found ourselves in a residential zone rich in greenery. The AI identified an area near St. Louis, a frequent location due to its central US location and the weighted averages being used. The prediction was 316 kilometers away, achieving 3,420 points. This highlighted a challenge, differentiating between similar residential areas across the US. While the bot did well this time, in later testings, it wouldn't not get so lucky. Landscapes are much easier to identify than buildings, so the bot performs much better on open areas than built-up ones. For the third round, we loaded into an environment with more prominent palm trees. I knew from the volume of them that it would be Florida. I also knew that it would be very unlikely the bot would agree with this. I anticipated a challenge, given the basic AI's ability to tell species of trees apart, and the area looking fairly green like the central US. The AI incorrectly guessed Oklahoma instead of Florida, resulting in only 717 points, due to the 1,617 kilometer error. This underscored a known limitation in handling specific states. A desert environment was next, nice and obvious for the bot to suggest a southwestern location in New Mexico. Although the actual location was a neighbouring state, the AI was fairly accurate, only 752 kilometers away, earning 2,027 points. The session concluded in a flat green farming area. The AI predicted Missouri, while the actual location was Kentucky. The distance was 517 kilometers, and the AI scored 2,688 points. This initial game set an impressive benchmark, with the AI scoring a total of 13,158 points, surpassing the average human score of 11,678 points. Subsequent games demonstrated varying degrees of success. The scores for the next 3 games were 12,551 points, 11,242 points, and 12,450 points, respectively, giving an average score of 12,350 points, indicating that the AI performs better than the average human player. However, specific challenges like distinguishing between coastal and urban environments highlighted areas for future improvement. This achievement becomes even more impressive when you take into account that human players can move around and look for certain clues, whilst the AI has one image to guess off. These tests not only validated the AI's enhanced prediction capabilities, but also illuminated specific challenges where further model refinements could improve accuracy. The mixed outcomes across different environments provided valuable insights into both the strengths and limitations of the model. The AI demonstrated robust capabilities across varying landscapes of the US, reflecting significant advancements in the predictive accuracy and reliability. While the model consistently outperformed average human scores, it faced challenges in accurately identifying locations with unique environments such as coastal regions and urban settings. These issues highlighted the need for ongoing refinement for the AI's ability to process and distinguish complex geographic features. Further iterations could benefit from incorporating more sophisticated machine learning algorithms and deep learning frameworks, whilst also training the bot on more than 22,000 images. These enhancements would improve the model's ability to learn from complex patterns and subtle cues within images. For instance, enabling the AI to differentiate between different vegetation could dramatically increase accuracy for regions like Florida. Technological upgrades such as enabling the AI to recognize RGBA images would refine the user experience, reducing pre-processing requirements. Overhauling the testing and training datasets to include global locations could elevate the AI's capability on a worldwide scale, enhancing its versatility and robustness. Finally, developing region-specific models could also improve accuracy by tailoring the AI to unique characteristics of different geographic areas. This project represents a significant step forward in my knowledge of the application of AI to geographic image recognition. The insights gained not only demonstrate the AI's capabilities, but also pave the way for future enhancements that could extend its application and accuracy. As the technology is refined and develops further, I look forward to uncovering new possibilities and surmounting the challenges that lie ahead. As we conclude, I'd like to express my sincere appreciation to my module convener Colin for his invaluable guidance and support through this project. His expertise has been instrumental in shaping both the direction and success of this work. For those interested in exploring more detailed methodologies, technologies, and academic resources referenced throughout this presentation, please refer to the list of sources provided in the description below. These references support my research findings and offer opportunities for further reading.